So to recap, yesterday we figured out what is concurrency, what is CPU bound and IO bound work, what's the difference between them. Also, we figured out that creating new threads is very bad, as well as destroying them. This is why .NET Runtime provides us thread pool abstraction that allows us to get free threads and to use them for our work. And we looked at some ways to schedule our work on thread pool using thread pool queue user work item and alternatively task run, which is better because task is an abstraction around the work, and this method is just use some delegate on a thread pool, and if some exception is thrown within it, it will crash the whole host. So today we'll figure out all the ways to create tasks and to manage them and what they are and how to effectively use them. So task is an abstraction around a logical unit of work, not around a thread. So tasks and threads are completely different concepts. When you use key user work item, you delegate this delegate to be executed by some free thread of thread pool. When you use tasks, there might not even be any threads. Because, for example, if you create task delay, it just creates a new task that will transfer from in progress state into completed state in 1 second, but it doesn't use any threads in the process. Here's an example of using tasks. So there are two, I'm creating two tasks using methods task run, and I'm passing this action delegate to something that will just block the thread 1 hour. So if I run this example, and then we pause our application, we can see that we have currently 2 threads from thread pool. We have 4 threads in thread pool. 2 of them are completely free. 2 of them are executing our do something method, in which it is staying on the method thread sleep. If we switch here on the parallel stacks window into tasks view, we'll see that there are 2 async logical stacks. It means there are 2 tasks currently in our application that are executing something. In this case, thread sleep. So in this case, it looks like tasks are somewhat similar to threads, right? Well, if we run a different example than this one that we covered yesterday, when we schedule 2 items of work on thread pool using queue user work item, both of which are just blocking the thread for 1 hour. When we pause it, we'll see that in the threads view, we have those 2 threads running task thread sleep. However, in tasks view, there won't be any tasks at all. Alternatively, if you create 1000 tasks, which will not do anything, for example, task delay 1 hour, you'll see 1000 async logical stacks on parallel stacks window in tasks view. But you will see that all of the threads of thread pool are completely free. They're not doing anything. So this is a way to manage your tasks and threads using parallel stacks window in Visual Studio debugging. When you run task, it has a status property. When you create a task, it has status property. The status property changes during the execution of the task. So when you just created a new task, it will most likely be in one of these 4 states. It means that it is currently executing. I'll cover every state in more detail in advanced meetup. For now, just know that when you schedule a task, it is in one of those states, like it is running or waiting for something. When it is completed, if it's completed successfully, it transfers into a state run to completion. If it is cancelled, it is transferred to state cancelled. If it is faulted, so some exception has been thrown inside it, it transfers into a state faulted. The task in this state, task can be in this state when it has been created, but it hasn't been even scheduled to run on a thread pool yet. How can it be done? Well, you can always create task like this using a constructor. New task, and then you pass a delegate there. However, this will create a called task, so it won't start executing until you call a method start on it. In .NET, most of the tasks are hot, so they execute as soon as you create them. And if you create task with method task run, if you create it with task factory, if you create it with any other means, it will create a hot task. Including the magic that happens with async await. When you write methods like that, the tasks that is returned from such methods are hot ones. The only way to create a call task is using the constructor, which is why this is very discouraged, and I propose never to use that construction, because first of all, yeah, you need to check if task has started, and only if it has not started, then to call this method, because if you call it twice, it will throw an exception. You cannot start already started task. That's first nuisance. And second, imagine that you have a method that returns task, right? So you just call this method and you await the result, or you wait for it, or you block on it, or something, right? Because you expect that this task is hot. Everyone expects all the tasks to be hot. However, if inside that method, the implementer of this method has created task in this way, this task will be called. And unless somebody calls task start method on it, it will never finish. It will never even start. So whenever you await on it, or if you wait for it synchronously, or if you block on it, you will just wait forever. You will block the thread forever, and it will never finish. This is why it's a bad way to create tasks like this. I just wanted to cover that there is such possibility. So yeah, so instead of thread sleep, like we blocked thread in a previous example, we can use method task delay. These two methods do absolutely the same, except this one blocks current thread until this timeout is expired. This one creates a new task, so this method returns a task. We can write something like var task equals task delay, and then we can use this task to get its status. We can await its execution. We can always also block the main thread. So this construction is absolutely the same as this one. It will block current thread for this amount of time. However, task delay internally just uses timers, so it creates a new task that is completed after this delay, and it doesn't use any threads at all. This task has a wait method that, that can be used to get to wait for its execution and block the current thread. If we throw inside the task, if we throw some exception, then tasks, like let's do this. Let's just comment wait and run this example. And this application will not fail. You can see that we checked its status after 1 second and it is faulted. So unlike queue user work item tasks do not crash the host. So if you suspect that some of the tasks can throw exceptions, you still want to use try catch inside the delegate that you pass into the task. So you can at least log that exception. If you do not log any exceptions here, they'll just be lost. You won't even know, and if you do not query this status, obviously, you will not just even know that something has failed inside the task. It silently swallows exception. So tasks can have results. So if you pass a generic parameter to a task, for example, string, this task will have a result of string that we can get after the task has finished executing. This is an example of running such task. We pass there a func delegate that returns string, and inside we just blocking the thread for 1 second, and we're returning this string here. So later, if we get the result of this task, this result property is basically the same as writing something like this: task1 wait, and then task1 result. So result property, it blocks current thread with similar in a similar way that task wait until that result is available, until task is transferred into a successful state. And then it returns you that result. So in this case, the result hello will be written into the console. So here we can see that from the first task, hello was written to console. So yeah, another method to get result is task get await or get result. These are helper methods that were added for when async await constructions were added to the language. Basically, async await use get awaiter under the hood. Thing is that if you throw an exception inside your task, then wait operation and result operation will also throw an exception. However, they will both throw aggregate exception, because inside the task there can be multiple child tasks that are attached to it, and all of them can throw different exceptions, although these exceptions are being aggregated and put inside aggregate exception of the task. So like if I throw here invalid operation exception, for example, and I'll just get the result here. We can see that the aggregate exception has been thrown. And inside that aggregate exception, the inner exception will be our actual exception. If you want to just your exception to be thrown instead of aggregate exception in the place where you synchronously block on the task, you can use get await or get result. This construction, unlike this construction, will throw the same exception, the first one, that has been thrown inside your task. There are ways to wait for multiple tasks at the same time. So imagine you create a task. For example, here we create 10 tasks that all wait for 10 seconds and then write done to console. Task has a static method wait all that accepts a list of tasks or any enumerable of tasks. And Also, task has a method waitAny that waits for any first executed task. So if we are only interested in the first task that has been executed and completely ran to successfully ran to completion, then we can use waitAny method to block current thread. This will block current thread until one of the tasks is executed. WaitAll will block current threads as well until all of the tasks are executed. Alternatively, I'll get to it a bit later, but I'll just show it right now. There are different methods, when all and waitAny. So notice the difference. Here we are waiting for it. So wait, it's blocking current thread. And here we are just subscribing to an event when something happens. So when all and waitAny, unlike these blocking operations, they again create a new task. So we can write something like this, var task equals when all. And then we can do anything with the resulting task. We can block on it, we can wait for it, we can await on it, we can run some continuations after it. But it will be completed only when all of the tasks will be completed. All right. There are different ways to create tasks from specific results. So imagine you need to create a method that returns task, but you don't need to run any asynchronous operations. You just want to create a new task that has already been completed and has some result inside of it. For that, task has static method from result. For instance, this construction creates a new task with generic parameter int and with a result of 3. It is already completed and ran to completion successfully when it is assigned to this variable. So you can use wait method on it. It will not block current thread, it will just return because it's already completed. And result will not block current thread, it will just return your result of 3. You can, by the way, use multiple wait and multiple result calls on the same task in a row without any problems. If you want to create a task that has faulted, you can use task from exception method that creates a new task that has already completed but unsuccessfully and is throwing an exception. So if here we call wait, it will throw an aggregate exception with this exception as an inner exception. And if we call getAwaiter getResult, then this line will throw this exception. Also, task has a property exception, which we can inspect. This property will contain the exception that happened inside the task. So in order not to throw it in our code. And another thing is canceling tasks. You can also create a task that has been canceled. We'll talk about canceling a bit later. But it creates a task that has been canceled, and inside this from canceled method, you can pass cancellation token so that it will indicate that this task has been canceled by this cancellation token. Another useful property is completed task. It just returns you a task that has already been completed without any result, just a completed task. It's a very good useful property because it's also cached by .NET runtime. So a new task is not created every time you call this property. It just returns you the same completed task. So whenever you need a task that has already been completed, you can just use this property and it will be very performant. So one more thing that I wanted to stress is that tasks are not magic things. Like we are used to think that it's a bit of a magic because we use a lot of async awaits in our code. But in case you do not use any async awaits, um, this is just a method that returns you a new instance of a class object named task. It's absolutely the same as if I wrote here a string or int or my custom class if I created my own classes. So what it means is that this method, it needs to create the instance of this task and return it to its caller. So in case of this example, we come here in this main thread. We are currently on the main thread. If I switch to threads view, we'll see that we are on the main thread. Here, this constructions means that we need to run this method. This method needs to return us the task, and the task should be written into this variable. So if we go inside, we can see that we are still on the main thread. It also executes completely synchronously. We create this task, for example, using this construction. This task is just a new instance of a task. We can sleep, which will block current main thread for 2 seconds. Let's do that. It blocks current thread for 2 seconds. We're still on main thread. We synchronously return this task into this variable. Now this task is in this variable. By the way, it's already run to completion because while we were waiting on the main thread, it executed in parallel. It just waited for 1 second and it wrote hello from background thread. If we inspect the console, we'll see that hello from background thread has been written by worker thread 12. And here we can just, I clicked something, no. And here we can just wait for this task, which will happen instantly because task is already run to completion. And we can finish execution. So task methods is just methods that return the instance of that class. It's important to remember this when we switch into async await discussion so that everything is understandable. Okay, let's switch to cancellation. Cancellation is a cooperative pattern in .NET. What it means is that we are passing some cancellation token in our asynchronous methods, and it's our responsibility to implement our asynchronous methods in such a way that they check if cancellation token has requested cancellation, then we need to cancel our operation. So this is a simple example of cancellation. We create a new cancellation token source, and then we are calling some method that returns a task, and we are passing there our token from property from our cancellation token source. And later, when we want to cancel this long running operation, for example, after we input something into console, we call the method cancel. This is how our long running operation can look like. We are just creating a new task using task run, and inside it, in background thread for forever, we are waiting for 100 milliseconds, and we are calling throw if cancellation requested method on cancellation token. You can, of course, check property is cancellation requested, but this is faster and easier way. And this is a proper way. Whenever cancellation has been requested, it's a valid contract to throw operation cancelled exception. This method does it for you. So it checks if cancellation token has requested cancellation, and it throws operation cancelled exception. It's important to throw operation cancelled exception and not just return, because if you just return, then task will be transferred into a completed state, and the consumer will not know if the task has completed successfully or if it has been cancelled. They will think that it has been successfully completed. If you throw operation cancelled exception, then the task will be transferred into cancelled state. And later, when you get await or get result, or you wait on it, or you get result, this property will throw operation cancelled exception if this task has been cancelled. So if you need to do that, or to block on task or get this result, or even await on it, because if you await, it will also throw. Make sure you catch operation cancelled exception if you expect that this operation can be cancelled. So cancellation, yeah, imagine that we have a very long running operation like this, which just thread sleeps for 5 hours. And we want to cancel it. But the implementer of this method is not us, it's just some library method. And inside this tasks that they created for us, they did not check any cancellation tokens. In fact, we cannot even pass any cancellation tokens. So this operation is running for 5 hours and we cannot do anything with it. However, we want to only execute this operation for 1 minute. And then we need to cancel it if it takes longer than 1 minute. How we can do it without any ability to pass here cancellation token? Well, here's the trick. We can create a new task, for example, using task delay. It doesn't use any threads of thread pool. It just works on timers again for 1 minute. And we can use task when wait any to wait either for the end of this task or for the end of this task. So then we can assign it to a variable, and we can wait for this task. So this operation will block exactly for 1 minute, because it will, after this task is finished, this operation will also be finished. Obviously, it doesn't stop this operation from running. This operation will still occupy one thread, and it will block it for the rest of 4 hours, 59 minutes. But at least we are able to continue execution of our flow. So that's a way to get around it. Alternatively, we can use task delay timeout infinite, right? Which is which creates a task that will never finish. Why would we want to do that? Well, because task delay accepts a second parameter of cancellation token. So now we have a task that will be completed instantly as soon as we cancel this cancellation token. Now we can use cancellation token in our operation. We just use when any, waiting for long running operation and for our infinite task. But as soon as we cancel our cancellation token, this task will already be finished. Cancellation tokens also allow us to specify some timeout here, so they will be cancelled automatically after this time. Also, if you do not need to pass cancellation token, you can also always pass cancellation token none, or alternatively just default, because cancellation token is a structure and default just creates an empty structure, and it's considered the same as cancellation token none. It's faster and shorter to write, so I prefer default construction. Also, how can we improve this example? Cancellation tokens can be linked, so you can link them together. Cancellation token sources. How it can help us? So imagine we have this code, and we are calling our method, our async method, where we pass our cancellation token. So this cancellation token we created outside, we pass it to the method, And whenever we cancel this cancellation token source, we want this method to stop executing. And in this method, we are calling this our long-running operation. We cannot pass this cancellation token to our long-running operation because it doesn't accept cancellation token. So instead, we create a delay task, like in previous example with timeout infinite, and we pass there our cancellation token, right? And here we create a task that will execute whenever either long-running operation or our delay finishes. So after our delay, if we cancel here cancellation token, then this cancellation token will be cancelled, the delay will also be cancelled, this task will finish, and this task will also be finished. However, we can do this, and we can create a new cancellation token source inside. And we can create another cancellation token source that combines our cancellation token source from outside and our local cancellation token. And as you can see, I'm using construction here. This is because cancellation token sources are disposable. And now we can pass the token from this combined cancellation token source to our task delay. So now task delay will be cancelled if our external cancellation token source cancels, or if our internal local cancellation token source cancels. Why do we want this? Because imagine if our long-running operation actually finishes in 1 second. So it finishes in 1 second. This task is also finished. We finish this task, and that's all. This task is finished. All looks good in theory. However, we created this task, delay, that is only going to be cancelled after this cancellation token source is cancelled. So we want to cancel it as soon as our long-running operation is finished. So what we can do is, after waiting for this task, we can check that if task is long-running task. So if the task that has completed, the first one, is actually our long-running operation, then we can cancel our local cancellation token source. And since our combined cancellation token source also contains this local cancellation token source, then this will cancel this task because this cancellation token source will be also cancelled. So this is an example where we might want to use linked cancellation token sources. Yeah, and just to remind you, since we just looked at cancellation, there is a separate method, task from cancel, that accepts cancellation token source and just creates a new task that has already been cancelled by this cancellation token source. So if you just need to create it synchronously, you can do it like this. Now, you obviously need to check for cancellation token if it has expired in your loops. If you have some long running operation, you need to manually implement cancellation in them. However, if you have very fast running loop, for example, like this, you are just counting I number for 100 million and then you reset the I to 1. It will run forever. It will run very, very fast. And if you add this line here, you'll notice that the speed of your loop has drastically decreased. It will be much slower because the thing also checks whether cancellation token source is cancelled or not, etc. So it's additional checks, it's additional logic in your very high performant operations that you need to be high performant. So what you can do instead, if you have a loop like this, you can check the cancellation token source, for example, only once per 10,000 iterations. In this way, you will still have high performance loop, but you'll be able to cancel it as soon as cancellation token source cancels. Well, as soon as next 1,000 ICE will be incremented. And yeah, whenever you create a new methods, just wanted to also talk about it. If you create a method that is returning task, the convention in .NET is to add an async postfix to it. So any method that returns task should have async postfix to it, so that consumers will know that this method returns you a task. And another good convention is to always have cancellation token supplied to this method, because even if you do not use it in your method anywhere and your method is fast, whenever you decide to add some logic inside or to call some other library that actually accepts cancellation token, you might want to pass this token into that library down to the stack. And if you do not have that parameter in your methods, you will need to add them, and that might be a breaking change if you have some interfaces that you need to change, etc. So whenever you have methods that you suspect you might need cancellation anytime in future, or even if you need it right now, consider adding that cancellation token. If you want your customers not to worry about it and skip passing it and do not even consider passing it unless they need it, you can always use default parameters like this. This would mean that they can call this method without passing cancellation token, and it will be just default by default. So it will never be cancelled. Now, one of the most important topics for understanding how async await works is chaining tasks, because moving on from the cancellation, it's chaining tasks because this is how tasks were chained in the past before async await have been introduced. So let's look at this example. There are two methods. One is called blocking code, another called non-blocking code. This is an example of methods that do absolutely the same, but one is blocking, creates a blocking task, another creates non-blocking task. So blocking task, it just creates a new task using task run, and it blocks the thread for 1 hour. So here we cannot do anything. It will internally block the thread for 1 hour. We can only wait for it, which will also block this thread with executing blocking code method. So it will already be two blocked threads for 1 hour. Non-blocking code, it creates a non-blocking task, which uses task delay. Instead of thread sleep, task delay constructs a new task that will be switched into completed state in 1 hour. It doesn't use any threads, it doesn't run anything in background. However, here we are also blocking on it inside this method. But notice that after we blocked in this method and we waited for 1 hour, we are just writing to console done from non-blocking code. So this is all we need to do. For example, we only need to write to console done from non-blocking code. How we can improve that example? We can create a new task that will take this task that waits for 1 hour and use a special method on it, continue with. Continue with method, it attaches continuation delegate to be ran after this task has been completed. It accepts previous task instance if you need it for some reason, for example, to get result or status of it, etc. And it will run this using another free thread of thread pool. So how would it work? This will create a new task that doesn't use any threads, and exactly in 1 hour, a timer will fire an event which will transfer this task into a completed state. And as soon as this task is transferred into a completed state, this continuation will be scheduled to be run on any free threads of thread pool. Free threads from thread pool will be selected, and it will run this code on some background thread. worker thread. This is how we create a non-blocking code, at least in the past when async awaits weren't introduced. This is how we can do it absolutely the same with async await. We just add async keyword before the task in our method. We create this task that will wait for 1 hour, that doesn't use any threads, with task delay. Then we await it, and then we write to console done from non-blocking code. Basically, what awaits does, in essence, not in the implementation details, because it actually creates a state machine, but in essence, to completely understand how it works, what it does is it attaches the rest of the method as a continuation to be run on some free thread of thread pool to this task after it has successfully executed. So this method and this method basically completely the same, almost. Here, task executing. After it executed, this continuation is run. Here, task executing. After it has executed, this continuation is run. This is how async await works in essence. We'll delve into much deeper details on it tomorrow. So just check. Yeah, there are some caveats about using continue with, because it requires detailed configuration in order to be executed exactly how you want. We also discussed it in the advanced section, but in 99% cases, same as when you, same as I told you, want to use task run instead of other methods. Same here, in 99% of cases, you want to use async await. You do not need continue with. It's just an old way to chain tasks. After async await has been introduced, it's a much simpler and more elegant way to write tasks. There are always use cases where you might need continue with, but we'll discuss its proper usage in advanced meetup. Two more things I wanted to discuss today. I hope we'll be on time. First one is task completion source. Task completion source is a class that allows us to create tasks that do not use thread pool at all. Well, tasks are abstraction about work again, not around threads. So they might use threads of thread pool. The same task might use 10 different threads of thread pool, or they might not use them at all. This is an example of how we can create task delay method manually. So we create a new task completion source. Task completion source has a property task. So if we just create a new task completion source and we check this task will be in not completed state. So we can await it, we can get result of it to block current thread. It will never finish for now because we didn't configure our task completion source yet. So task completion source has a method setResult. SetResult method will transfer task completion source task status from not completed state into completed state. So if some other code will call this method and you are here awaiting for this task, the await operation will finish and you'll get its result if you need a result, because task completion source has generic parameter if you want to create tasks with the results. This is an example of how we can create an analog of task delay. We are creating a new timer. It's timer object from system threading. And inside the timer, we are telling it that it needs to wait for 5 seconds. And after 5 seconds, it needs to run this code. And this code just runs CCS setResult. So here, if you wait for this task, we'll see that it blocks current thread for 5 seconds, and then it successfully finishes. Yeah. If we want to rewrite this example without using tasks, we can use this async await code, very, very simple and naive. So in while loop, we are just incrementing I for 50, and we are waiting for 100 milliseconds. So this thing will basically wait for 5 seconds every 100 milliseconds. It will request another free thread of thread pool to run this continuation, because this continuation needs to be run on some thread. And after, it will again return this thread to thread pool, and it will wait for 100 milliseconds, and it will request another thread from thread pool to run this continuation. And after this operation is done, it will set our task into completed state. One more thing about timers, since I showed it here. This is a class that allows us to schedule some delegate to be executed in some time. Thing is that it runs its delegate using queue user work item method. But as you remember, queue user work item method crashes the host if it throws an exception. So if you need to use timers, make sure you try catch any code inside that can throw an exception. Otherwise, your whole host will crash if exception is thrown. And another thing I wanted to discuss is task yield construction. So, and a feature of tasks, well, we already delving a bit into async await constructions, but anyway, whenever you await any task, so it's the same as scheduling this continuation to be run on some other thread of thread pool, on free thread of thread pool, after this task is completed. The task that is returned by this method, which just returns this task. So to simplify, we can just, I guess, do this. So it creates a new task that just blocks some background thread for 1 second. And here we are awaiting it. And what await should do, it should schedule this continuation to be run on some background thread after this task has been executed. However, if this task is already in completed state when await happens, then the rest of the method is just being run on the same thread which called await. So no continuation is attached to this task at all. It just runs as completely synchronous code. So what await does, await checks if task is in completed state. If it's in completed state, it just continues execution of the rest of the method. And only if it's not completed yet, this part will be attached to the task. This is important thing to know when you're designing concurrent applications, because let me just show you this example. I made some mistakes here. So you can see we are on the first main thread. We are on the first main thread. I forgot to step into the task. We go inside that method. It should create our task that we'll wait for. We are writing to console thread doing something from the main thread. We're still in the main thread. Now we are blocking the main thread for 2 seconds, just because, I don't know, we needed to do some synchronous operations here. We are writing this from the main thread again. Now we are awaiting the task, and we expect that this continuation will be run on some background thread, with some expensive synchronous operations. However, as you can see, when we step on the next line, we are still on the main thread. And we are still on the main thread here, because this task has already been completed. It runs only for 1 second, but here we waited for 2 seconds before we even started awaiting this task. There is so you can see that in console, all the operations were executed by the main thread. And only after these all operations have been done, the instance of this task has been returned here, and we started waiting for it. If you need to make sure that the continuation is run on some different thread, there is a quick fix for it. It's called task yield. What task yield is in essence? Task yield method, it creates a new task that is not completed yet. So it's not in not completed state. So if you await it, then .NET will be forced to attach the rest of the method as a continuation to this task. However, as soon as this task is scheduled for execution, it transfers into completed state. So as soon as it schedules, it transfers into completed state, and continuation is scheduled straight away. So it's almost the same as writing task delay 0 or something like that. And only task delay 0 will actually probably be completed before you even attach the continuation. But task yield always ensures that it yields this task to be executed by thread pool. It will not continue the rest of the method to be executed synchronously. So now if we run this example with task yield construction on the top of the method, we'll see that as soon as we started doing something here, we're already on the 7th thread. So all of these operations inside this method after task yield were performed by worker thread. And one more thing is that you might have noticed sometime in the past, or whenever you investigated tasks, that task is disposable. And we do not dispose of them anymore. Well, this is correct thing to do, because task is disposable historically, because it contains a reference to wait handle. And this wait handle has been used in methods like wait all, when all, methods that wait for many tasks, but only in .NET 4, even when we didn't have async awaits yet. In .NET 4.5, the usage of this wait handle has been reduced to a minimum, and in .NET Core, it's pretty much non-existent, unless very, very corner cases. Basically, this disposable is not needed anymore. So it doesn't really make sense to call the disposable. It will only litter our code with garbage and will make it unreadable. And it will not bring anything to the table, because it will not do anything at all. It doesn't do anything unless wait handle is used. And wait handle is used only in very rare cases. I'm not sure even in which ones, because I tried to research it, and it looks like, at least in the latest .NET Core, it's not being used anywhere in any of the APIs that I am aware of. All right, so I guess if anyone has any questions, now would be the time to discuss them. So I guess if nobody has any questions, then see you tomorrow on Async Await.